recall, like last lecture, we derived the field integral representation of the partition function for a generic many-body Hamiltonian with bosonic or fermionic operators. So we derived that the partition function can be written in terms of a field integral, like generalizing the path integral from quantum mechanics. Again, an integral over all field configurations, which now here have certain boundary conditions which I didn't write down, but which are periodic for bosons and antiperiodic for fermions. And each field configuration is weighted by an action, which is given here for, again, a generic Hamiltonian consisting of a two-particle term, a non-impacting contribution of Hij and some particle term which represents interactions. So what we are going to do now is to discuss several examples for this. Like for the rest of the lecture, we will discuss examples of this. So we will discuss. So there are many examples. So what I decided is, I mean, I said, so one can now also be more conceptual and discuss now how to do, for example, perturbation theory in this term and so on. But as you said, we would like to already see some examples. So what we are going to do is to discuss examples where we consider fermions. So we start out from, let's say, electrons in a metal, and we will discuss different cases. So I don't know if we managed to do all, but the idea would be first to study the weakly interacting electron gas, then to see like somehow instability arises, which leads to magnetism, that's the Stoner instability, leading to itinerant magnetism. And the third example would be superconductivity, another instability which leads to superconductivity. So I don't know if we managed to do all of them, but at least what we will do for all of them, if we manage, but the procedure will always be like starting from some action in terms of, let's say, where these then are the electrons, try to first apply perturbation theory in some diagrammatic analysis, which I will then introduce always like the parts which are important just for the specific example, and then we have to see what is known, what is not known, so if we can extend it. So try to understand what is going on from let's say, analysis of Feynman diagrams, and once one has seen like what is the relevant physics, what is like the important structures to keep the relevant physics that one is considering, then one can start out and derive an effective theory. So this is what, like ideally we will do for the three cases. Start out, let's say for the weakly interacting electron gas, make an analysis of the interaction terms in terms of Feynman diagrams, and then see what is the relevant like degree of freedom to derive an effective theory, and do this also for the case of magnetism and superconductivity. Now this is all cases of fermions, so ideally we would also discuss bosons, but probably I'll next semester just continue like this lecture, and then we can do all that ones. But this will be the plan. However, first, before doing all this, we have to do some more reminder. This is like what we will always be dealing with. So once you start out from the partition function, or also said that this can be generalized to some generating function for correlation function in terms of integrals. Well, mostly what we will be doing is always Gaussian integrals. So I just recalled like the three different kinds of important Gaussian integrals that are like the key for all the calculations. So this is the three cases. So we can have bosonic variable, which just means that we have some, real numbers or complex numbers. So this would be real or complex bosonic variables. So let's say there is an element from the Rn vector space. So one needs to know this expression for Gaussian integral. This will be like the central object for the real bosonic field. Now the complex bosonic field, one has a similar expression, and this can be just derived using this, separating, for example, the real and imaginary part. So you see here you get the determinant to the -1/2. So this is what we already encountered also in the path integral fluctuation determinant. For the complex bosonic field, you get kind of this for the real and the imaginary part, so you get the determinant to the -1, and then the exponential of this. And for the fermionic case, so this I think is one of the exercises to show that you get the inverse of this here, so inverse of 1 over the determinant, you get the determinant, but then the exponential, you get also this. Okay. Now this is very important because this would be a kind of a sketch of the generating functions that I mentioned last lecture briefly. So if you're interested in expectation values of components vi and vk with respect to such a Gaussian integral, you can generate them by differentiation with respect to the source. Okay, so let me just give some more formulas very briefly, because they will be important, although in the examples we will always concentrate on the fermionics. I mean, all the examples that I mentioned, still going to discuss all 3 cases. So in all cases one can define an expectation value with respect to, let's say, the Gaussian weight. Well, this is very symbolic. So what I mean is, we define an expectation value where we have an integral over, and this now here stands for either of the 3 cases, so the real bosonic, complex bosonic, or fermionic. Okay, so there in the real bosonic this would be integral over dv, then v transpose av, and this here would be like the function that you want to take there. Okay, and then I have divided by 1 over n, which would be just this integral here without the source, which is the normalization factor. Okay. So I hope this is clear. Okay, so this stands for all the 3 cases. So it could be dv, then it would be just this way. Could be dv dagger v, then it would be this way, or it could be x psi bar psi, then it would be this way. And then we can define an expectation value in this form. Okay, so this is just to introduce a notation. So one can then actually just by using this and differentiating with respect to, let's say, component Jn and Jm, one can generate this correlation function, okay? So this will be a to the -1 and m if we are in bosons, real bosons. Now we can do the same for the fermions. Then the only term that contributes is if we take here the complex conjugate. Okay, if we would have this here, this would be just 0. So we have to pair or look at the expectation value of the variable in the complex conjugate, and we can define the same for the fermionic fields, where again we have to take psi and psi bar to get something finite, and this will be again into. Okay, so this will be one important thing that one will use. So again, you can prove this easily from these right-hand expressions by differentiation. So what one gets is one gets matrix elements of this inverse operator. Okay, so this will typically in the applications then will be the propagator of the non-integrating theory. Okay, so here's typically the Hamiltonian with some energy. So you get the inverse matrix elements will be the propagator of the non-integrating theory. Okay? So this is all the same. Now, if one looks at higher order correlation functions, then one has something more interesting. So if I look in the bosonic case at the 4-point correlation function, well then this will get 3 different contributions. So you have kind of big theory which tells you you can pair this with either one. Okay, so this gives you one expression, then pair the other one. Okay, so I could pair these 2. Let's say a to the -1 kl, a to the -1 mn, or I can pair these 2 plus a to the -1 km, a to the -1 l, and I can this. So is this known or is it like this? I don't know if It's clear what I'm talking about. If I say you can pair this with this, or that's known, like for Gaussian integrals. Yeah, okay. If you again want to prove it, you can just do this by differentiating this expression here. Okay. Now this would be the real bosonic case. In the real in the complex bosonic case, again, such an expectation value would be 0. What you have to do is you have to have, to get a finite contribution, you have to have the same number of variable in the complex conjugate variable. Because this is the only one that, the combination that appears here. So this is a dagger, no complex conjugation and transpose. The only combination that appears, and then you see the difference to here is why we could pair this with any of the three. You can now pair this only with this or this. So you get, instead of 3, only 2 contributions. So you would get a to the minus 1 k m, a to the minus 1 ln, or a to the minus 1 kn, a to the minus 1 lm. Okay, so that's the difference between the real bosonic and the complex bosonic. Now, if we would look at the corresponding Grassmann expectation value of, let's say, 4 such fields, like a 4-point correlation function. Again, to get something finite, you have to have the same number of variables psi and psi bar. And now it is as in the bosonic case, you can only pair this with this, or this with this. So we can copy this from here. But then we have to be careful with signs. Like, if you want to, again, derive it, you can just use the formula given there. Now, like the hand-waving way to see it is like, what you have to do is, if you want to arrive at this expression here, you have to pair this with this. So you have to put this variable on this side here, okay? And to get this term here, you want to pair this with this, so you have to get this expression on this side here. So what you will see is that if you put this here, you get a minus, because they're anticommutative. If you put this here, you will get 2 minus, which is plus. So you will get here minus and here plus. Okay? So that's the difference between the real bosonic, complex bosonic, and the Grassmann correlation function. So quadratic, for the quadratic correlation function, all the same, but here comes the difference. Now, it's good to generalize all this, and this goes under the name Rick's theorem for like general endpoint correlation functions. Okay, and I just write down once the generalization of this, which means you have to see like how many contributions you get from an endpoint correlation function. Well, the number is different for this and these two, because you get different possibilities for interaction, and then here you still have to take into account sign factors. So if you generalize this, you arrive at very important formulas. So in general, theorem, and this is the basis for later on applying perturbation theory. Okay, so this is will be used heavily, but I already want to introduce it here for all the 3 cases, because later on we will use it just for the Fermi solution examples. So separating again the 3 cases of real bosonic, you can have, let's say, an expectation value of 2n such components, and this is then, by generalizing this, given by all possible pairings of these indices p1 to p2n, so all possible pairs that you can form, and then what you get is, well, the inverse of n products of all these pairings. Okay, so this is maybe not the most transparent, but one way to write it. This amounts to looking at all pairs, all possible pairs you can form from these, and every pair defines some two indices, and what you get is the inverse operator at these two. So the matrix element of the inverse operator at these two indices, and you have to sum of all possible pairs. With here, now, if you look at the corresponding complex case, again, two n variables, and of the two n variables, n have to be of type V, and the other one of V bar, which the bar here stands for the complex conjugation. And if you look at such an expectation value, then again, I mean, the difference is that now you can contract, like, take this with any one of these, and so on. Okay, so what you get is the sum of all permutations. And then you get, again, n product of n terms, which are matrix elements of this inverse operator. And here's the sum over all permutations of n integers. Sum over all permutations of n integers. So I hope one can read it, but the idea is, well, you can pair this with any of these, and then once you have chosen one, then this can be paired with any of the remaining, and so on, and this just amounts to taking J1 with any of these indices, and you can then perform a permutation in the second index. No? This just corresponds to all the combinations. And what you always get is a product of n terms, which are matrix elements of the inverse operator here. Okay? And now if we generalize this still to the fermions, we will get again the same structure as here, but we have to be careful with the signs. Okay? So that's the only thing that matters, is now we have to take into account, well, there can be signs appearing depending on like how you have to reorganize here these terms to put always those close to each other which you want to like contract to form such a. And if you go through it, you can convince yourself maybe. It's the following. So the only difference that should appear to this formula here is some sign factor, and I will just write the result and then try to motivate it. Is that you get again the sum p a to the minus 1 j1 I p1 a to the minus 1 j n I p n. Okay, so this again stands, just copying this to take j1 and then I and the permutation operating on 1 and here permutation on n. Okay, so this is getting all the combinations. And then you get a sign factor which here corresponds to the sign of the perturbation. So it's an even or an odd number of transpositions. And why I could write this in such a compact form is that actually, if you look at this, how I organize them is in a different order here. I wrote them in J1 to J2 to Jn, and then use here the inverse order, In to I1, okay? So you can see, for example, that so if I want to have like the J1 and the I1, then this would already be in the right order, okay? Because this would be like J1, J2, I2, I1, okay? So to get the I1, I would get like, have to shift it twice, I would get a plus, and this is important with this. So you have to be a bit careful that here I wrote the increasing order from 1 to n, and here the decreasing order, and this is, if you go through the, I mean, I home carefully, so that explains here the sign thing. Okay? So this will be very important formulas if we do perturbations here in this term. Okay, so this is what we will later do for examples. Like one way to try to evaluate this for an interacting series. Well, if we have a non-interacting series, we understand everything. I mean, it just amounts to Gaussian integrals. But this quartic term actually prevents us from doing an exact integral here, so we don't know how to treat it. So one thing always one can start out to try to see is to see, let's try to understand the interaction in terms of perturbation series. So then you would expand from the exponential this interaction term, and this then will give rise to all these kind of expectation values, where this expectation value is then with respect to the non-interacting series of these field integrals. Okay, so there will appear then products of inverses of this operator, and this is just the propagator of the non-interacting series. Okay, so this will how this will appear then once we put this to work. Okay, questions or? Okay, so this was still some technical things, and now I just come to the applications that we want to discuss. So now I go back actually to some basic physics again, and the idea is to evolve along examples and more of these technical issues, depending on how much is known already or not, is to see then how much to go into detail. Can you erase this or? Yeah. Certo.
Só você expõe, eu não tive tempo de olhar a última aula, só que você discutiu. Você discutiu, você só colocou.
Não, bom, o que a gente está discutindo aqui é a generating function para um grand canonical ensemble. Então, na verdade, é muito complicado calcular dentro de um canonical que o number é fixed. De certa forma, é mais fácil para a gente estudar o caso que, bom, o número de partículas é conservada, mas a gente está discutindo um sistema aberto que você pode tocar troca de partículas com os reservoirs, com o ambiente, e então a gente tem que introduzir o potencial químico como um Lagrange parameter que vai fixar a média do número de partículas. A realidade que a gente precisa para assim, a maioria dos problemas, também, graças a Deus, é mais fácil de calcular. Então, para a gente é simplesmente, assim, como vocês aprendem na física estatística, o potencial químico é como um Lagrange parameter correspondente à conservação de partículas que aqui tem no sistema, que quando é carregado nos ferros é mesmo como uma charge conservation.
Nesse caso, é o operador número mesmo?
Não, é operador número mesmo. Número, porque realmente é aquela coisa, você sabe que sua partition function exponential, density operator exponential de todos os operadores que representam uma quantidade conservada. Então você tem energia, você tem temperatura que fixa a média de energia, e a gente tem particle conservation, então é número operator que conserva, e o Lagrange parameter é a potencial química. Eles já ligaram lá, não, né? Não. Não sei se respondeu a pergunta para falar a verdade.
Qual é a melhor para calcular melhor?
Tá, tá. Então a gente realmente está simplesmente estudando por enquanto a Grand Canonical Partition Function, onde você tem um número de partículas conservada, mas tem um reservoir que permite a troca com partículas, então o que a gente fixa é o número médio através do potencial químico. Tá. Talvez também fica mais claro se a gente agora vai nos exemplos. Okay, so just an outlook, like of what ideally will follow, but I'm not sure how far we will get, but this would now be applications, and we will here concentrate first on fermionic systems, so we will consider the interacting Fermi gas and instabilities. And these instabilities should become hopefully clear throughout the lecture what is meant by instabilities. Okay? So in this, ideally, we will discuss three applications, which is first the interacting electron gas, or the weakly interacting electron gas. And discussing this will already allow us to introduce one of the main concepts first, which is diagrammatic perturbation theory, and then in the second step will allow us to introduce kind of Hubbard-Slartonovich transformations, which is like the tool to derive effective theories. So once we have done this program for the weakly interacting electron gas, we will consider instability, and this is the Stoner instability of the interacting electron gas, and this will lead to metallic magnetism, and again we will follow like the canonical steps. First look at diagrammatic perturbation theory, discover some instability, which will then identify some relevant degrees of freedom in which we will derive then the effective theory by means of Hubbard-Slartonovich transformation. And this will be one. And the second one will be another instability, which is the Cooper instability, which is another instability of the interacting Fermi gas, and instability which gives rise to superconductivity. And again, just do like follow the general scheme, so introduce the model, do some diagrammatic perturbation theory, discover some instability, see what is the relevant channel or the relevant degree of freedom in which to derive an effective theory, derive the effective theory. So we will do this in 3 steps. This will need some technical points, so diagrammatic perturbation theory and this Hubbard-Slartonovich transformations. Now, in the ideal world, after that one could study bosonic systems. And it's always the same, like do first diagrammatics to get some feeling on what is going on. Once one has some idea of what is going on, one can derive the effective theory. Then the next step would be to make some better analysis of the effective theory by renormalization group. So I'm thinking to maybe just continue next semester, maybe not twice a week, but once a week. So, but we have to see, like if there's enough interest, I guess I will just then follow once a week with the rest of the program, then bosons and then RG. So as one has done this. But so for now, we will concentrate on this. So we will pretty sure be able to discuss the whole program for the weakly interacting electron gas, and I also think for the Stoner stability. Now for superconductivity, I'm not so sure how far we get, but okay. And all this, so as we combine, so we'll go through like the general program, that's it, but it now depends a lot like on the interaction, because you have to tell me like where we have to go into more detail and where not, okay? Because some things already known, but I don't know how much is known. But to actually come to this more interesting things, let's first talk about the Fermi gas, or what we here always have in mind is just a metal. Okay, so let me just review some very basic things about metals. so that you kind of know what we're talking about and what it's going to be. So let's first take a couple of steps back and consider the metal as a clean electron gas. Let's say the preparation. So let me see what I want to say here. So our starting point is that we will have some pictures. So what we're talking here, in fact, is about like say, electrons in a metal. Okay, and these are instabilities of electrons in a metal. So let's first start like with the model that we have in mind to model electrons in a metal. So in a real metal, of course, there's a lot of things going on. So there's interactions among the electrons. There's interactions with the lattice. So you have interaction with some phonons. You can have impurities in the system. You can have disorder. So there's a lot of things going on. So let's first define like what we will concentrate on. So we will concentrate on some idealization for the moment, that we say we don't care about disorder, so we consider a perfect clean system. So effects of disorder can become very important in low dimensional systems, in low temperatures, but let's forget about it. One thing you can argue is because we're, mainly interested here in 3D systems, and disorder can be very relevant in low dimensions. Then the second point is that well, you have, of course, the lattice itself, the ions which form the lattice, and there's interactions, there's phonons, but let's not consider these, okay? So let's just talk about like the electrons in moving freely and interacting with them, and this is the notion of the clean electron gas. Still, one has to take into account, well, that, the electrons are charged, but the overall system that we are considering is like charge neutral, so the electron charge is just compensated by the ions of the lattice. So we consider this, that these electrons which are charged are moving against a positive background, which make everything charge neutral. But apart from that, we will just consider, let's say, free electrons interacting with each other, and that's all. Okay? So let's see. Okay, let's write some things. Not everything. Okay, so let's say we consider metal as of the order 10 to the 23, positively charged ions forming the regular lattice. And then you have same electrons moving between them. Then these electrons interact among themselves, so they're interacting via Coulomb interaction. But apart from that, in principle, they can scatter off, or they will scatter off. That is oscillations. Oscillations is 12. Oscillations, which are the phonons, so once you quantize them, interaction between electrons and the phonons. They can scatter off lattice imperfection. And quite a lot of things going on. And of course, if one sees something, I mean, one has an experiment, one has to see what is responsible for the thing that one observes. So in general, one has a problem where one has interactions. One has this order, and one has the lattice still with its own dynamics. One has different sources which make the problem highly complicated. And we will not try to address all of the problems simultaneously, but we will consider just a set, mainly now first the interacting part. So motivation is that at low temperatures, typically the phonons can be neglected. So you can forget the motion of the lattice ions and just consider again that they're forming some positive background to make the system overall charge neutral, but we do not have to consider typically at low temperature scattering of phonons. So what we mean here, phonons can be neglected. So what we consider, the ions are motionless. And their positive charge can be thought of as smeared out to form a positive background against which the electrons move. Form a positive background against which electrons move. Okay, so the idea here is, like, of course, the ions form some regular lattice, but in the end, what we're like typically after is physics on a low energy scale, it stays set by temperature, so on larger length scales which just do not resolve, like lattice spacings or something. So we're interested in low energy theories where we cannot resolve like the real lattice, and then we can just think of the ions for the low energy theory just as something positive smeared out background against which the electrons move. This is also called, I guess, the Gillian model or something. So this is one thing. The second thing is that this order, so it often leads to interesting quantum interference phenomena. Interesting quantum interference phenomena. But they are specifically relevant in low-dimensional systems. Four-dimensional system, one or two, quasi one or quasi two-dimensional systems, low and let's say concentrate, or we will concentrate here mainly on three-dimensional systems. So there some motivation that we can neglect these effects, or just take the idealization that we have a real perfect system that we are walking at. So here's 3D and idealization of in a clean system. Okay? So that's saying, motivating a bit why we disregard these and these. Now I have to be a bit more careful, because once we come here to the superconductivity, actually the lattice will enter again as a main player, because we will first see that the lattice will provide some effective interaction between the electrons, which is attractive. And this then leads to the Cooper instability. So in this point, we should actually reintroduce the lattice as a main player to derive the Bezier theory for superconductivity. Now, this order itself is also very interesting. We have to see if maybe we can look at it in some exercise, or like if there's a continuation, then this will be also discussed. Like non-interacting electrons in this order environment are also very interesting, and there one can also again follow like the canonical way, and you first look at perturbation theory, diagrammatic, see what is interesting, and then once one has derived or found the relevant degrees of freedom, derive an effective theory for disordered systems. So this is also something interesting, but if we will come to this only in some exercises or in some future continuation maybe. Okay, so this is some kind of motivation why we, for the moment, forget about this and this. And if we do this, we arrive at the notion of the clean electron gas, which now is described by Hamiltonian. That's the one we will now concentrate on to discuss these two issues here. So we have a Hamiltonian, which consists of two parts. And it's also called the Jarion model, where H0 stands for the non-interacting part, or this is given by the sum over spin up and down. Then the DDR integral, so typically we'll look at E equal 3, but let's keep it general. So this is just, for convenience, I just don't write vectors. Okay, so this is just, yeah, so I should put over there vectors, but I just don't do it anymore. Cool. This is just a free part, yeah? Kinetic energy, force up and spin down, and then you have, this one here? So, oh, this is like sigma corresponds to spin up and spin down. So it's the sum for spin up and spin down. It's not readable. Okay. No. Okay. Yeah. Okay. So it's sigma spin up or spin down. Yeah. And the interacting part, sigma and sigma prime mean spin up and spin down. And then equals dr prime. There's a sigma r, there's a sigma prime r prime, a sigma prime r prime, a sigma r. Okay, so that's the class of Hamiltonians that we have considered like in the general way. So we have a non-interacting quadratic term, and then we have a quartic term which counts for the interaction. So interaction of the spinful electrons, sigma, sigma prime, sigma prime, sigma prime, and the interaction potential, or the potential is just the Coulomb interaction. So Q of R is E squared over modulus of R, and I have set all these factors 4 pi epsilon and so on just equals to 1, okay? Just using this kind of conventions. So this is the idealization that we have, I mean, these free electrons just non-interacting with this order lattice, but among themselves, and then we have to take into account still what we said here. Well, we don't take into account the lattice dynamics itself, but we know that there's a positive charge background which makes all of this charge neutral, and this is to saying that the Q equals 0 component, the homogeneous component of this interaction potential is just 0. Okay, so this corresponds to the charge neutrality, that this is the potential of the homogeneous configuration is just compensated for by the positive background. It's called charge neutrality. The presence of the homogeneous sphere-out background. Okay, so maybe make just 5 minutes break and then let's see. So the idea is, let's then start like with the very basic. So what we want to do here, we want to understand actually, so what we want to calculate is the ground state energy of the weakly interacting electron gas. Okay? And the idea is, well, we have to understand what is like the ground state and what are the relevant excitations in the system. So how to address this? Well, we will try to first look at the ground state energy by doing perturbation theory in the interaction term. This will lead us to introduce also this diagrammatic perturbation theory. However, before we come to this, we should first just briefly recall what the non-interacting ground state and ground state energy and so on looks like, and then based on this we can then try to understand what are the excitations in the interacting gas. So this is what we will do, like the rest of the lecture, just briefly recall the non-interacting case and then maybe start formulating like the procedure how we will introduce the interacting cases and like what we are doing. Okay, just 5 minutes.